Hello again, everyone. Welcome to our discussion of section 3.4, where we will talk about the zeros of a polynomial. Last time we talked about graphs of polynomials, where the zeros of a polynomial were, we saw that there are x values for which the polynomial value will be equal to 0. So in this section, we'll learn how to find those x values. Now, in that section, the previous section, we already had each polynomial given to us in factored form. Remember that? And before we go deep into this subject, I want to remind you to please read or review the section before you watch this video. So skim through the section, maybe no more than 45 minutes, and then watch the video or attend the class and review the lecture notes and attempt to solve all the problems you see in the book or in my lectures without looking at the solutions, and of course complete all the homework assignments by the due date and review throughout the course. Okay, so remember last time we graphed a polynomial like this. So we were given a polynomial such as this, right? And we graphed it. So what we did was set each one of these factors to 0. We found where the zeros were, like that. Like that. So all these are the zeros of the polynomial. So if you plug these values into each factor, you get that factor to become equal to 0, and the whole polynomial will equal 0 at those x values. Now what about, so in this case we were given all these factors. In every case we were given the factors. But what about if you have a polynomial like this? Like this one. X cubed minus 7x squared plus 14x minus 8. This is not in factored form. So in this section, we will learn how to manually find the factors of a polynomial like this. It takes a bit of time. It's tedious work, but there is a procedure to find the zeros of zeros, or in other words, the factors of a polynomial like this. Okay, in this section, we will look into that. Okay, so the methodology works like this. Suppose you have a polynomial like this, then the rational zeros, so we will talk about, in the main topic would be the rational zeros of a polynomial. Okay, and those are the values that x can take in order for the polynomial to be equal to 0. So the procedure begins with finding all possible rational zeros. All possible. That means if you have 10 possibilities that could be the zeros of a polynomial, maybe 3 of them will work. But you can there's a way to find 10 possible candidates for the zeros of a polynomial, but out of that 10 or 8 or 5, maybe 3, 4, or 2 will work. Okay? So the first step is find all possible rational zeros of a polynomial, and from that pool of possible rational zeros, we will have to test each one to see which one will actually work, which one is actually the zero of a polynomial. That is, which one actually, when replaced for x, will make the polynomial equal to 0. Okay. So we have, this is the formula basically. Once you have a polynomial, the key word here is possible. That means this formula will give you the potential rational zeros. Not that all of them will work, but some of them will work, not all of them. So the possible or potential rational zeros of a polynomial, P, can be found with this small formula. Factors of the constant term, that would be that one. So if I box this polynomial, factors of the constant term, that would be for -8, right? And then divided by factors of the leading coefficient. And the leading coefficient in this case has factors plus or minus 1, right? The leading coefficient is the coefficient of the polynomial term with the highest power. And x cubed is the highest power. So the coefficient of it is 1, positive 1, but positive 1 has factors 1 times 1 and also -1 times -1, right? -1 times -1 will give us +1, which is the coefficient of this leading term. Okay, the leading term in a polynomial is the term with the highest power. The coefficient of the leading term is the leading coefficient. So we find the factors of the constant term, that one, and divide by the factors of the leading coefficient. Okay, so in this case, in this particular case, the constant term is -8, right? -8. So that -8 has factors plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. So we have 12 or 8 different factors of this -8 term. So if you multiply, for example, +8 times -1, you will get -8. If you multiply -8 by +1, you get -8. If you multiply +2 by -4, you get -8. If you multiply -4 by +2, you get that. So these are all the factors with which we can obtain. We can multiply them by each other and get -8. Okay? Those are the factors of the constant term. Now, at the same time, the leading term is x cubed, and therefore the leading coefficient is 1, which has the factors plus or minus 1, like I was saying earlier. -1 times -1 is +1. 1 times 1 is +1. So then the possible rational zeros are, as this formula suggests, are the factors of the constant term, -8, divided by the factors of the leading coefficient, which are the plus or minus 1. So these numbers divided by these two will give us these. So these are, what you see in the middle of the page here, are the possible rational zeros. Not that all of these will work. In fact, it's impossible that all of these will work. Do you know why? Because in any polynomial, the highest power tells us about all the zeros that the polynomial can have. So if you have the highest power 5, let's say, the most number of zeros you can have is 5. If you have x cubed, in this case, then the most number of rational zeros you can have is 3. Because suppose you find 2 of them. Where's the third one? Well, the third one is not a rational zero. It's a complex number. Okay? So the maximum number of rational zeros for this polynomial cannot exceed 3. So that means these 8 potential ones, these 8 potential zeros, at least 5 of them will not work. That's assuming the other three are rational zeros, not irrational zeros or complex zeros. Okay? So we can quickly know that not all of these will work. We already know that because of the power of this polynomial. At least 5 of these factors, 5 of these 8 factors will not work. So what happens when you find the potential zeros? What do you do with these? We know that we find these by finding the factors of the constant term and dividing them by the factors of the leading coefficient. That's how we find these. But what do we do with them now? Well, the next thing to do is plugging each one of these, positive 1, negative 1, positive 2, negative 2, positive 4, negative 4, positive 8, negative 8, into the x in this polynomial and seeing if the result is equal to 0. If it is, then that number which we plugged in for x to get the 0 is considered a 0 of a polynomial. Okay? So it's a tedious process, and when I had to do this for an article that I published a long time ago, I used the Excel software. So technology helps a great deal. Nowadays, you have computers that would do this in a matter of seconds, but please note these methodologies come to us from centuries ago where there were no such technology. So that's why such methods were highly useful at that time. Mathematicians could find the factors and zeros of the polynomial in the matter of minutes, okay, even without the technology. Okay, so continuing on, please read these because I've tried to, as I'm sure you've noticed by now, these worksheets are not just examples for us to do in class or practice with. They're also summarizing. I've also summarized the contents of your textbook from each section in these worksheets. So it's instead of reading 5-6 pages, maybe you would read this in a more concise way, in a matter of maybe 1 or 2 pages. So please take the time to read this material as well as your textbook, because your textbook opens this stuff up. It's not in compact form like this, and it gives you examples that are different than the examples we solve in these videos. Okay? So you have those examples. In addition to those examples, you have these examples. In collection, in combination, they'll give you sufficient number of examples to look at and to learn from. So other things we want to know before we see some examples is that the degree of a polynomial is the highest power of the variable in the polynomial. So in this case, the degree was 3 because that's the highest power. Okay, so that's what it is, the degree of a polynomial. Therefore, testing of the 8 rational zeros in the above example can stop when we find a maximum of 3 zeros of the polynomial. So what this paragraph, short paragraph, is saying, it's saying that you can have a maximum number of 3 rational zeros in this polynomial. So if you test these numbers one by one, and if you find 3 rational zeros, then and you haven't finished testing all the other numbers, you can simply stop, because the other numbers you know will not work, because you've already found as many rational zeros as is possible in this case. Okay. The implication of finding the zero of a polynomial, the implication of that is that each of these zeros can help us find a distinct factor of a polynomial, and you'll see how it works today. Okay. For example, in the above polynomial, that's that one, in this polynomial, the rational zeros were identified as 1, 4, 2. So as in this list, positive 1, positive 4, and positive 2 were tested or replaced in this polynomial, and it was found that those three numbers, 1, 4, and 2, will make this polynomial equal to 0. So, if that's the case, then x minus 1, x minus 4, and x minus 2 are going to be the factors of this polynomial. So that's the real reason why we really look for the rational zeros of a polynomial in order for us to write the polynomial in factored form. Okay, that's the real reason. So remember that these, remember that the formula for the factors of a polynomial is x minus c. So we have x minus c as the formula for the factors. So if you have 1 as the 0 of that polynomial, if you have 1 as the 0 of that polynomial, then the factor would be x minus 1. If you have 4 that you plugged in for x and obtained 0, then the factor would be x minus 4. If you substituted for x with 2 and you got 0, then x minus 2 would be the factor of that polynomial. So whatever the 0, you say x minus that value as the factor of the polynomial. And that's why you see that these are the zeros of the polynomial, 1, 4, 2, but the factors then would be x minus 1 times x minus 4 times x minus 2. Okay, so this polynomial, with this procedure that we explained, finding the factors of the constant term, finding the factors of the leading coefficient and dividing those by each other, and then testing each of these numbers in the polynomial, that yields this factoring of the original polynomial, which is pretty neat. And last time we learned how much it will make graphing polynomials easier once you have them figured out in factored form. Okay, all right. So last time we also talked about multiplicity. Remember that? We said that if the multiplicity is even, that means the power of each of these factors. So in this case, the power of all of these factors is 1, which is an odd number. If multiplicity of a factor, or a 0, a multiplicity of a rational 0 is odd, then the graph of a polynomial will cross the x-axis at that point. At that x value, the graph of the polynomial will cross the x-axis because that 0 has multiplicity odd, has odd multiplicity. So look at all these zeros or factors. They all have 1 as power. So the multiplicity of all these three zeros, 1, 4, and 2, is odd. That means at x equals 1, at x equals 4, and at x equals 2, the graph of the polynomial will cross the x-axis. Okay? If it was even, if any of these factors had even power, then the multiplicity would be even, which means at that x value, the graph of the polynomial will not cross the x-axis, but it will touch the x-axis and bounce back to the same side. Okay? And we talked about what that means. We said that if you have even multiplicity, I'm going to just to do a quick a sketch. So if you have even multiplicity here, even multiplicity, then the graph is going to hit that point and bounce back to the same side, the graph of the polynomial. If that 0, let's say x equals 2, has even multiplicity, or x equals 3, it makes no difference. If x equals 3, which is that, has even multiplicity, the graph will do that. Suppose this is x equals -3, right? Suppose that's also a zero of the polynomial. Then that means the polynomial will hit that point and cross it with odd multiplicity. Remember that? I'm just reminding you about what we talked about last time. So odd multiplicity, the graph will cross the x-axis. Even multiplicity, the graph will touch that x-axis at that point and bounce back to the same side. If the line is coming from this side, it'll touch it and bounce back to the same side. Okay. Okay, so continuing on with our discussion here. So this is, on this page, again, you have a reminder of what we talked about. So note, in the graph of a polynomial, an odd multiplicity indicates the graph of the polynomial will cross the x-axis at the 0. So here, and with the even multiplicity, it will not, right? It will bounce back to the same side. So here I have an example. Notice that this piece of graph is associated with this polynomial. And notice that each of these factors have odd power, 1. So the -6 and +7, which are the zeros of this polynomial, right? -6 and +7 have odd multiplicity. So at both of those points, the graph of the line, notice that it has crossed the x-axis at those points. It'll cross the x-axis at that point because that's 0, -6, and +7 have odd multiplicity. In contrast to that, here in this example, you have one of the zeros, which is -6, that has even multiplicity. Look at the power of this. This graph is associated with this polynomial in factored form, right? So -6 is a 0 of the polynomial. The multiplicity is even because this power is even. So at -6, the line of the graph of the polynomial will touch the x-axis but will not cross it. It'll bounce back to the same side. Okay? But this point, at +7, right, at +7, you have a multiplicity odd. The power of this factor is 1, which is odd. So the graph will cross the x-axis at that point, like that. Okay. So this is why we bother to factor polynomials. They help us with graphing the polynomials and knowing exactly what the zeros of a polynomial are. Okay, so let's see an example of, we'll look at a couple of examples of how this procedure works. Okay, you will see these in your homework. Maybe if the coordinator of this course decides to give an example of this kind on an exam, maybe you'll see one short example like this on an exam too. But it won't be any question you see in your exams won't be as lengthy and as detailed as the examples you see in these worksheets or in the homework problems. Okay, if you see an example on an exam, it'll be a short one, not too big or detailed like these ones. These are just for us to practice and understand what the concept is. Okay, so here in this example, It says find and list all possible rational zeros, okay, of this polynomial. Well, the leading term in this polynomial is x to the 4, right? And the coefficient of that is positive 3. So it has factors plus or minus 1 and factors plus or minus 3. Okay? The constant term, positive 4, has factors plus or minus 1, plus or minus 2, plus or minus 4. Right? So what are the possible rational zeros? We divide these terms by these terms. Okay? So we divide all of this by plus or minus 1. We get plus or minus 1, plus or minus 2, plus or minus 2, plus or minus 4. Are we done? No, because we have to divide all of this by plus or minus 3. So plus or minus 1 divided by plus or minus 3, plus or minus 1 over 3. Plus or minus 2 by plus or minus 3, plus or minus 2 over 3. Plus or minus 4 divided by plus or minus 3, plus or minus 4 over 3. Okay? So these are all possible rational zeros of this polynomial. Will all of these work? Is it possible that all of these work? Absolutely not. Because how many do we have? We have 2, 4, 6, 8, 10, 12. We have 12 possibilities for rational zeros. But how many maximum rational zeros this polynomial can have? Look at the highest power. It's 4. So the maximum number of rational zeros this polynomial can have is 4. So we already know 8 out of these 12, 8 of them are impossible for us to accept. Okay? We can have maximum number of 4 rational zeros. We cannot have all 12. So is it possible for all possible rational zeros to be valid? Why or why not? So the answer is no, right? Just like I mentioned, no, because we can only have a maximum of 4 rational zeros given the degree of the polynomial. Okay? The degree of the polynomial is 4. That's the highest power of the polynomial. So we can have a maximum of 4 of these acceptable. The other 8 will not work. Then it says find each actual zero of the polynomial and use it to factor the polynomial one step at a time. Okay, so let's try the easiest one, plus 1, right? So testing x equals 1. We have like that. And so if we calculate this number, what do we get? We get 3 plus 8 minus 9 minus 10 plus 4. Is this equal to 0? So we have 3 plus 8, 11, plus 4, it's 15. 15 minus 19 is equal to minus 4, which is not equal to 0. So this x equals 1 is not a rational 0. Okay, let's try negative 1. Testing x equals negative 1. Okay, I'm going to substitute in the polynomial. You can see the polynomial up here. So 3 times minus 1 to 4th power plus 8 times minus 1 cubed minus 9 times minus 1 squared minus 10 times minus 1 plus 4. So minus 1 to the 4th power is positive 1 times 3 is 3. Minus 1 cubed is minus 1 times 8 is minus 8. Minus 1 squared is positive 1 times negative 9 is negative 9. Right? Minus 1 times minus 10 is positive 10 plus 4. Okay? So we have 14, right? And 17, that's positive 17, minus 17, we end up with 0. So correct. So this x equals negative 1 is a rational 0. So what would be the factor then? So the factor from this rational 0 would be x plus 1. Okay. Now if you solve this, if you set this equal to 0 and solve for x, you get negative 1. Okay, so this is one factor of this polynomial. Oops, I'm off like that. So this factor is a factor of that polynomial. So now that we have the factor, one factor figured out, we can divide this polynomial by this using the synthetic division, actually. Using the synthetic division, we can divide this polynomial by this and find the other factor, which would be a polynomial. So let's do that. So I'm going to, and we learned about synthetic division last time, right? So using synthetic division, let me move this up. So using the synthetic division, we have, here is, so I'm going to, so the coefficients will be 3, and we have all the variables, right? So there's nothing skipped. So I don't have to put 0 anywhere. So I'm going to write down 3, 8, negative 9, negative 10, and 4. 3, 8, negative 9, negative 10, and 4. Those are those coefficients with no gap. See, we have power 4, power 3, power 2, power 1, and no power, no x, right? So there is no gap. So we don't put a 0 anywhere. So it's 3, 8, negative 9, negative 10, and 4. And what about the c? What would be this? Well, this is x plus 1. So c must have been negative 1. Okay? So using the synthetic division, we bring this down, 3. 3 times negative 1, write it here. 8 minus 3 is positive 5. 5 times negative 1, negative 5, sorry. 5 times negative 1, negative 5. That's negative 14. Negative 14 times negative 1 is positive 14. Positive 14 minus 10 is positive 4. 4 times negative 1 is negative 4. 4 plus negative 4 is 0. And that's our remainder. So this is the remainder. So because our polynomial, original polynomial had the highest power of 4, in the synthetic division, this will give us 3x cubed. Let's see, no, actually, yeah, we can do that. So 3x cubed, and then plus 5x squared minus 14x plus 4, okay, and 0 would be the remainder. Okay, 0 would be the remainder. So now, so given that, we know that all of that gives us this. So this, we know that this times x plus 1 is going to give us the original polynomial. So the original polynomial p of x is equal to that. Okay? So using this procedure, we found that x equals -1, or factor x plus 1, is a factor of the original polynomial. Then we use the synthetic division to find the other factor. So x plus 1 times that will give us the original polynomial that we have. Now we can look into factoring this because we're not done. So just to make this shorter, because there are 12 different numbers we should check. So I showed you how to check one by one. I checked 2. That's how we check. We have to check to find the other 4 factors of the other 4 zeros of this. Okay, the other 4 zeros. So now to find the other factors of the polynomial, we can try any of the other ones that we haven't yet tried. That is plus or minus 2, plus or minus 4, plus or minus 1/3, plus or minus 2/3, plus or minus 4/3. If you try these into this polynomial, you should be able to get a 0 for whichever one that is the 0 of the original polynomial. In other words, this polynomial and this polynomial have the other any other rational 0 that this might have, that this polynomial might have. We know that x equal to -1 is already, we found that. So among the ones we haven't yet tested, among these ones, whichever one that works in this polynomial will also work in this smaller polynomial. So we can check one of these. And I've already done this. So we can check. Let's check the one that I already know will work or should work. Let's check this one. Positive 1/3. We will check that one. Okay. Let's check positive 1/3. Okay. So I've already checked plus or minus 2, plus or minus 4. They do not work. So we're going to check plus or minus 1/3. Okay. Let's do that. And I'm going to do that with this one. So with this, testing x equals 1/3. Okay. I think that it was this one that I checked and worked, not the -1/3 one. But we'll find out. So testing this in here, in this polynomial, let's plug in. So we have 3 times 1/3 cubed plus 5 times 1/3 squared minus 14 times 1/3 plus 4. Okay, so this would be 3 times 1 over 27 plus 5 times 1 over 9 and minus 14 over 3 plus 4. So this will be 3 times 1 over 27. It'll be 1 over 9 plus 5 over 9 minus 14 over 3 plus 4. Okay, let's see. So we have 9 as the common denominator here. And then we have, oops, let me move this up. 9 as the common denominator, so we have 1 plus 5 minus 42 and plus 36, right? So we have positive 42 minus 42 over 9, which is 0 over 9, which is 0. So it checks out. So x equals 1/3 checks out because it makes this polynomial equal to 0. That means it'll make this original polynomial equal to 0 as well. So I'm going to write that here. Testing x equals 1/3. Then we have 3 minus 14 times 1/3 plus 4. And then this is equal to 0. So I'm just going to write down 0 because my space is a little bit limited here. But as you saw on this sheet, on this scratch paper sheet, we will get 0. Once we do the algebra on that, we will get 0. So x equal to 1/3 is a 0 of the polynomial. That means the factor is going to be x x minus 3x minus 1, I should say. 3x minus 1 is a factor. Okay, the reason I say this is because when you set this, so that's the fact, when that's x equals 1/3 is the 0, then the factor has to be 3x minus 1. The reason I say this, if you have any questions about that, it's because of this. If you set 3x minus 1 equal to 0 and solve for x, what do you get? You get 3x equals 1 and x equals 1/3, which is what we used, right? X equals 1/3, which is what we used in this polynomial. Okay, so x equals 1/3 being the 0 of this polynomial, it means the factor 3x minus 1 must be a factor of that polynomial. And that's the justification for that. So you work backward. If you know this is the 0 of the polynomial, you find the factor of the polynomial like that. Because what equation set equal to 0 will give you x equals 1/3? That equation. So that is your factor of the original polynomial. Okay, so now we have another factor here of this polynomial this time. Okay, so now we can divide this polynomial by this factor to find another factor of this. So we're breaking it into pieces by finding one factor of this, which we just did by testing x equals 1/3, and this 1/3 came from our original breakdown of the factors, all possible factors of this polynomial. So testing all of this, you'll figure out that, okay, that doesn't work, that doesn't work. Oh, that one works, so 1/3 worked. And so that gives us another factor. So now I can break this up. I mean, you can go on trying these in that. You can do that. You can try the ones that didn't work. I mean, the ones that you have not yet tried in here to see which one will make this 0. But it seems that it's easier if you use the long division and synthetic division to find the other factor. Okay? In this case, we have no choice but to use the long division because as we discussed in the last video from the previous section, the coefficient of this x in the divisor is not +1. It's other than +1. So it's +3. So we must use long division to find the other factor. So let me do that up here. So this is you can see any of these examples is quite involved because we've already used that formula which we introduced in this section, the factors of the constant term divided by the factors of the leading coefficient gives us the possible rational zeros, right? The possible rational zeros. That's what these are. Then we use the synthetic division. Now we're going to use the long division. So there's a whole host of tools that we're using to answer this question, to find all the factors of this polynomial. Okay? So I'm going to do that up here. Up here. So using the long division, this is what we have. So we have the this polynomial, right? I'll try to fit it there. 3x cubed plus 5x squared minus 14x plus 4 divided by this factor, 3x minus 1. This one. Okay, let me move this up a little bit. Divide by this factor. So 3x minus 1. Okay, so just like what we learned last time, ignore, disregard all those terms. Think about a term you can put up here such that if you multiply the 3x by it, you get 3x cubed. So obviously you already have 3 here, so you don't need to put a 3 there. You have an x here, so all you need is put in x squared, right? X squared times 3x will give you 3x cubed. So let's do that. X squared times 3x. Now we have to distribute this to both terms. So we just cover that. We compare the first terms in the divisor and the first term in the polynomial to figure out what this term should be, which we figured out x squared. Once we figure out what that term should be, we're going to multiply it by all the terms in the divisor. It doesn't matter how many terms. Sometimes you might have 3 terms here. You would multiply this by all the 3 terms and write it underneath this and subtract it from above. So x squared times 3x, it's going to be 3x cubed. X squared times minus 1 minus x squared. As soon as you run out of terms to multiply x squared by, then you would put a parenthesis around this and put a minus in front. Now let's subtract these. So 3x cubed minus 3x cubed, these add up to 0, right? 5x squared minus x squared. Minus x squared is positive x squared. So 5x squared plus x squared, it is 6x squared. 6x squared. Do we have any x terms here or a constant here to subtract from those? No. So we're going to write this down as it is down here. Minus 14x and plus 4, right? So this becomes irrelevant because there's nothing here to subtract from the x term and from the constant. So we just write them down as they are here. Okay, so now, once again, we repeat that step. We cover those two terms. Compare this with this first term in the divisor. What should we put up here such that if we multiply it by 3x, we get 6x squared? Well, we already have 3, so we're going to need a 2, right, to give us 6. So plus 2. 2 times 3x is 6x. We want 6x squared. So we also need an x next to that. Okay? All right. So 2x times 3x is 6x squared. 2x times minus 1, minus 2x. As soon as you run out of terms to multiply 2x by, put a parenthesis around this and put a minus in front. So now, let's subtract. 6x squared minus 6x squared is 0, right? So those two terms end up 0. Minus 14x minus 2x. So minus 14x minus 2x is positive 2x plus minus 14x. We get minus 12x. Is there any constant here to subtract from 4? No. So we're just going to write down the positive 4 as it is. Okay. Now, once again, cover that, all the other terms. Focus on the first term. What should we put up here in order to multiply it by 3x and get minus 12x? Well, we should have minus 4, right? If I put a minus 4 up here, minus 4 times 3x, it's going to be negative 12x. Okay, so now we're going to distribute the minus 4 to both terms in the divisor. Minus 4 times 3x, minus 12x. Minus 4 times minus 1, positive 4. As soon as you run out of terms in the divisor to multiply by negative 4, put a parenthesis around it and put a minus in front. Then we're going to do the subtraction. We have negative 12x minus 12x. This minus will make this positive 12x plus minus 12x. They add up to 0, right? These add up to 0. 4 minus 4, 0. So we have 0 remainder. So we found a full factor of this polynomial, but we would expect that because we already knew that this is a factor of that. So we knew we're not going to have a remainder. So this quotient is our final factor of this original polynomial that we started with. It's our final factor because if you try to factor this, you're not going to be able to find any rational zeros of that. Okay, this one has no rational zeros, so it'll have a complex 0. It'll have a complex 0, which in this section we're not considering. Although complex numbers are coming up next in the next section, in this course we will briefly, we just talk about it once in that next section, but then they will come up again and again if you're taking other higher level math classes, especially those of you who are electrical engineering majors. You will see complex numbers again and again. Okay. All right. So now we can write down the final factorization of this original polynomial. Let's do that. So the P of x, the original polynomial that we had, P of x, has these factors. It had this factor, remember? Remember that we tested x minus 1 and it ended up making the polynomial equal to 0. So the factor was x plus 1. So that's one of the factors, x plus 1. Just to be efficient, I omitted testing these numbers, but I already tested these numbers. They did not work. So the one that worked was x equals 1/3. So that's the one I showed you guys to see how it will work. So if you plug in x equals 1/3, you end up with 0. And we ended up with this factor. Once we found another 0, we found the factor, another factor, which would be 3x minus 1. And we used this as a divisor for this polynomial, and we found the other factor, which is this whole quotient. Okay? Once again, once I found this factor, I used this factor, this 0 and this factor, to divide this polynomial by this factor, which led us to this new quotient, which is the new factor. So all of this is our next factor. So let's write it down. X squared plus 2x minus 4. So there. So this original polynomial, 3x to the 4 plus 8x cubed minus 9x squared minus 10x plus 4, we could write it using these factors. If you expand this, if you multiply all of this together, you will get that original polynomial. Okay, so nowadays, this might not seem as a great big feat, but remember, these techniques are coming to us from centuries ago, so hundreds and hundreds of years ago, this was a big deal. Without a computer, they were able to factorize a polynomial. Okay, like that. So now we know exactly where the zeros are. We can graph this polynomial if we wanted to. Okay. Okay, so let's do another example. So here, once again, we have a polynomial like that. 2x to the 4 minus 7x cubed minus 8x squared plus 14x plus 8, and they want us to find each rational 0 and use it to factor the polynomial one step at a time. Okay, so we already know that this 2 is the leading term is 2x to the 4, right? We know that because it has the highest power in this whole polynomial. This term is the leading term because it has the highest power. So the leading coefficient is the coefficient of the leading term, which is 2. So that has factors plus or minus 1 and plus or minus 2. Right? So the constant in this polynomial is positive 8, and positive 8 has these factors, plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Okay? Now we can divide using that formula that we talked about on the first page. Using this formula, factors of the constant term, these guys, divided by factors of the leading coefficient, these guys, will give us possible rational zeros. Okay? So let's do that. So dividing all of this by 1, we get, so these are the possible rational zeros. All of this divided by plus or minus 1, we get these back, right? So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, comma. Now all of this divided by plus or minus 2. Plus or minus 1 divided by plus or minus 2 will get plus or minus 1/2. Plus or minus 2 divided by plus or minus 2, we get plus or minus 1. It's already there, so I'm not going to write it again. Plus or minus 4 divided by plus or minus 2, we get plus or minus 2. So it's already there. Plus or minus 8 divided by plus or minus 2, it's plus or minus 4. So I'm not going to write it again. So we have 2, 4, 6, 8, 10 possible rational zeros. So right now we haven't tested any of these. So any one of these can make this polynomial equal to 0 if you plug in for x. Any one of them. Okay? So I already tested some of these. Let's see. So we have yes. So let's try the ones that I know will work, because if we don't, we're going to be sitting here trying all of these. But the procedure goes that we would try plus 1 here to see if we get a 0. We would try negative 1 here to see if we get a 0. Then we would try plus 2 to see if we get a 0. Then minus 2, plus 4, minus 4. We would try all of these 10 different possibilities to see which one will lead to 0. Now, what is the maximum number of rational zeros we can have here? Can you tell? Well, the maximum number of rational zeros will be equal to the degree of the polynomial, which is 4. So for sure, we know 6 out of 10 of all of this will not work. So which 4 will work, which 4 of these possibilities will work, we'll have to test one by one. Now, I've already tested, so I know that the minus 1/2 will work. Minus 1/2 will work. So let me show you how that, for example, that step would work. So testing x equals minus 1/2, right? What do we have then? Let's plug in into this polynomial. The polynomial at minus 1/2 is equal to 2 times minus 1/2 to 4th power minus 7 times minus 1/2 cubed minus 8 times minus 1/2 squared plus 14 times minus 1/2 plus 8. Okay? So then let's simplify. We have 2 times minus 1/2 to an even power 4. That will make this negative positive. 1/2 raised to 4th power is 1/16. Minus 1/2 to an odd power like 3, that'll be minus 1/8. But minus 1/8 times minus 7, it'll be positive 7/8, right? Minus 1/2 squared, that'll be 1/4, positive 1/4, times minus 8, it'll be minus 8/4. Minus 1/2 times 14, it'll be negative 7 plus 8. So what do we end up with here? Let's simplify. 2 times 1/16, it will be 1/8. That's 7/8. Minus 8/4 is minus 2. Plus minus 7, that's minus 9. Minus 9 plus 8 is minus 1. Okay, so let's, and then if we continue, what do we get? 1/8 plus 7/8, it's 8/8 minus 1. That is equal to 1 minus 1 equals 0. So this checks out. So using that, That's x equals minus 1/2 is a 0 of that polynomial. We just showed it. So the factor, that means the factor of this 0 is equal to 2x plus 1. That's the factor. Okay. Some of you might have questions about how is that? How do we know this is the factor? Well, set this equal to 0. If you know an x value is the 0 of that polynomial, then you're looking for a factor such that if you set that factor equal to 0 and solve for x, you get x equals negative 1/2. Okay? So, if we set this 2x plus 1 equal to 0, and then solve for x, what do we get? We get 2x equals minus 1, x equals minus 1/2, which is what we have here as the 0. So once you figure out the 0, then figuring out the factor is easy because you're looking for a factor such that if you set it equal to 0 and solve for x, you get the 0. X equals minus 1 over 2, which is the 0 of that polynomial. Okay? So we work backward. You use this to work backward and to find the factor, as I did. Okay? Just think of what factor, when set equal to 0 and solve for x, would give you the x value you had. Okay? And that would be 2x plus 1. Okay. So now, since we figured out that this is a factor of this polynomial, we know we can divide this polynomial by this factor using, of course, long division, because this x in the divisor has a coefficient that is not equal to positive 1. So we cannot use synthetic division with this. We must use long division. So we already know that if we use the long division, divide this by this factor, we will get a full factor with no remainder. So let's find what that other factor is using long division. Okay. Using long division, we have this scenario. Let me like that. So I'm going to divide that polynomial use my black pen. Too much blue in here. 2x to the 4 minus 7x cubed minus 8x squared plus 14x plus 8 divided by this factor, 2x plus 1, right? 2x plus 1. Okay, so like before, we want to know, cover all those terms, look at this term. What should we put up here in the quotient such that if we multiply it by 2x, we get 2x to the 4th? Well, we already have the 2, so all we need, and we have 1x, all we need is x cubed to multiply by this, to get this, right? Okay, so x cubed times 2x, we get 2x to the 4th. X cubed times 1 plus x cubed. As soon as you finish or run out of terms in the divisor to multiply by this term in the quotient, and put a parentheses around them, around those terms, and put a minus in front. Okay. So now let's subtract. 2x to the 4 minus 2x to the 4 that'll be 0. Minus 7x cubed minus x cubed, that's minus 8x cubed, right? Minus 8x cubed. And then the other terms, the x squared, the 14x, and the constant, we have nothing here to subtract from them, right? So we're going to write these down as they are. So minus 8x squared and plus 14x plus 8. Okay, so once again, we're going to cover all those terms and ask ourselves, what should we put up here to multiply by 2x and get negative 8x cubed? Well, that would be minus, we need a negative 8, right? We have a 2. So minus 4. And then we have minus 4 times 2 is negative 8. So we need x cubed, but we have just x. So also minus 4x squared. Okay. So now let's distribute negative 4x squared into both terms in the divisor and write it underneath here. So minus 4x squared times 2x minus 8x cubed minus 4x squared times positive 1 minus 4x squared. So now subtract. So this minus 8x cubed minus 8x cubed, so that will be minus will be positive, right? So these two add up to 0. Minus 8x cubed, x squared, minus 4x cubed. That this minus will make this positive 4x squared, right? Minus 8x squared plus 4x squared will be minus 4x squared. Okay, and then the 14x and positive 8 don't have any x term or constant here to subtract from them. So we're going to write these as they are. So plus 14x plus 8. Okay, once again, we covered those. The rest, we just focus on the first term here. What should we put up here such that if we multiply it by 2x, we get minus 4x squared? Well, we already have 2, so to get minus 4, we need minus 2. Minus 2 times 2x is minus 4x. So we need another x. Minus 2x times minus 2x, it'll give us minus 4x squared. So minus 4x squared minus 2x times 1 minus 2x. Like that. And then with a minus in front, right? So minus 4x squared minus 4x squared. This minus will make this positive 4x squared. Added to a minus 4x squared, we end up with 0. Then 14x minus 2x. So this minus will make this positive 2x. Add to 14x, we get 16x. And 8, there is no constant here, so plus 8. Okay, positive 8. So now, once again, we covered that 8. We just focus on the first term here. We ask ourselves, what should we put up here such that if we multiply it by the 2x, the first term in the divisor, we get 16x. Well, we have a 2, we need a 16, so positive 8. 8 times 2x is 16x, right? So we have 16x 16x, 8 times 1 plus 8. Okay, as soon as we ran out of terms in the divisor to multiply by 8, we put a parenthesis around that and put a minus in front. Okay, great. So now let's subtract. 16x minus 16x, 0. 8 minus 8, 0. So we end up with no remainder, which we expected because 2x plus 1 we knew is a factor of this polynomial. So now this quotient is, as a whole, this whole thing is another factor of this polynomial because we know this whole quotient times 2x plus 1 will give us this polynomial. Okay, so let's write down that here. So the original polynomial, so thus the original polynomial p of x is equal to 2x plus 1, which is this divisor, times the quotient, times this whole thing. Right? So times x cubed minus 4x squared minus 2x plus 8. So if you multiply this factor by this factor, you will get this original polynomial. Okay? But now let's see if we can, this is already factored, fully factored, this one, right? We cannot decrease this to any smaller factor. How about this one? Now this one is an interesting case because we could, one way to find, for sure this has factors, for sure. Because look at the list of possible rational zeros, right? So there are other numbers here that would give us the factors for this. But one way would be that. One way would be test other numbers, that other possible rational zeros in this factor to see which one would make this equal to 0. But something interesting happens here because if you notice, we have 4 terms in this polynomial, right? And in the past, in earlier sections, we said one way to factor a polynomial with 4 terms is by grouping. So let's try factoring by grouping. Like I said, you can keep trying these numbers. You can keep testing these numbers here to see in here to see which one would make this piece equal to 0. And then that would give you another factor. You can either do that, or if you notice that you have 4 factors, and try factoring by grouping. Grouping because we have 4 terms. Okay, so let's do that. So from the first 2 terms, what can we factor out? X squared, right? So we can factor out x squared out of these 2, and then we're going to group these 2 together. So group 1, group 2. Okay. From the first group, factor out x squared. What do we have left with? X minus 4, right? From this one, from the group 2, factor out minus 2. Minus 2 times x minus 4. Interesting, isn't it? Now, it worked because factoring by grouping, now we are able to fully factor that expression without trying any of the other possible rational zeros. So then we have x minus 4 and x minus 4 as common factors. So let's factor out x minus 4 times x squared minus 2. So from that, from here, we end up here. And from here, we end up here. Okay? Using factoring by grouping. And we can stop there. This will give us a nice full factorization in combination with that, right? So now this factor times these two factors give us the full factorization of the original polynomial. So let me write that up here. So the polynomial, this is the original polynomial, is equal to this factor, 2x plus 1, times x minus 4, times x squared minus 2. Can you even expand that more? Yes, you could. Right? You could do that. So either this, I personally would stop there, but if you want, you can factorize that even more using the special product formulas. So you could say, or the polynomial is equal to 2x plus 1 times x minus 4 times x plus square root of 2 times x minus square root of 2. So that'll give you the full factorization. I would stop there because that expression does not have a square root numbers in it. It doesn't have any irrational numbers in it. But you can go further and write down, factor that last term again and say x plus square root of 2 times x minus square root of 2. Okay, so that's the, either one would be the final answer in this case. Okay, so we have come to the conclusion of another section. When we come back in the next section, we will talk about complex numbers. Until then, have a nice day, and I'll see you again next time.